Hello, welcome to this lecture on biomathematics. We have been discussing statistical thermodynamics and its application to biological systems. We discussed about energy, entropy, and we briefly mentioned something about free energy. We said that energy is basically the energies that we see, that we know, like the spring elastic energy to pull like a spring pulling, or van der Waals energy, or electrostatic energy. So we know energy that we knew about energy well before, and yesterday we learned a bit about entropy, and we said that entropy can be quantified by saying that entropy, defining it as entropy is a quantity proportional to the number of possible states. And we could count, if we could count the number of states, and we call it omega, we defined entropy as, so we said that entropy S is Kb log omega. And this is when all states are equally possible, or we also wrote an expression minus Kb sum over I Pi log Pi. So, where Pi is the probability to be in a particular state I. Then you can ask the question, what is the probability to be in a particular state I? We will discuss this today, but this is, we know that if you know this or this, we can calculate entropy according to this formula. Now, let us think a bit about probability to be in a state and so on and so forth. So, today we will discuss two quantities. So, the title of the lecture is basically Statistical Thermodynamics of the Biological System Part 2, and we will talk about some quantity called partition function and free energy. So, we talked about free energy already. Now, we will talk a new quantity called partition function. Before talking that, let's understand that we said that the importance of free energy, we briefly mentioned that any system eventually will go to a state of equilibrium, and we define something called equilibrium. When something is in equilibrium, we can say that a system is in equilibrium when the free energy has a minimum. So, if you compute the free energy of the system, and if the free energy is minimum, if some places you might have studied that the change in free energy delta G has to be 0. When delta G is 0, or the free energy G itself is minimum, or the change in free energy is 0, at that point we can call this as equilibrium. So, we yesterday mentioned F as free energy. Some places you have to, in biology very often you might have seen this notation G. In the coming lectures we will discuss what is the difference between G and F. So, you might have heard Helmholtz free energy, Gibbs free energy, and so on and so forth. So, we will discuss what is the difference between all these terms, but the concept of free energy is, in generally it is true. So, we said that the concept of free energy, yesterday when we discussed, we said that the free energy is nothing but, we use the notation F, the free energy. So, this is free energy, and this is the interaction energy that we know, this is like Coulomb energy or spring energy depending on the system. This is the energy that the potential energy or the interaction energy minus temperature times entropy. So, the free, and whenever F is minimum or delta F is 0, you will lead to equilibrium. So, this is the definition of the equilibrium. A system is in equilibrium when the free energy is minimum or the change in free energy is 0. We told that if you plot free energy as a function of any parameter, and for whatever that parameter value you will have this minimum, and this is the point where the system is in equilibrium, and we will discuss about this equilibrium in detail, but this is the importance of free energy. By knowing the free energy, we can know whether the system is in equilibrium or not by calculating either delta F or delta G. So, we will discuss that, but the point you all want to, I want all of you to note is that the free energy, the quantity that determines whether the system is in equilibrium or not, has energy and entropy. So, it is not enough to just know energy, you have to know also entropy. So, that the combination of energy and entropy is what decides free energy, and the free energy is what decides many other things. We will see that free energy decides many of the properties that we measure. When we do an experimental measurement, all the measurable quantities that we discuss basically will be determined by the free energy. So, if we know the free energy, we can know many of the quantities, we can guess, we can understand, we can learn many things about many of the quantities. Okay, so, we have two quantities, energy and entropy, and a combination of both is required to understand about the system. Now, there is a new quantity which I will discuss, which is called a partition function. So, this is partition function, and this will be denoted by this Z. So, what is Z? So, it turns out that the definition of the partition function is that it is sum over all states where beta, I will explain this in a minute. So, if you take exponential of the energy multiplied by beta, beta is basically 1 over kBt, or this can be written as e, or this is same as sum over I e power minus EI by kBt. So, if you know that, and I is where, so if you imagine that if system is in state I and the energy of the system is in state I is EI, you do this, if you know this energy of the system for every state, you exponentiate it e power minus beta times EI, where beta is 1 over kBt, kB is Boltzmann constant, T is temperature, and if you do this sum, what you get is this quantity called partition function, and this has a relevance in the sense that now there is a relation between partition function and free energy. That is what we will go discuss in a minute, but just understand this bit more, how to calculate partition function. So, if a system has many states, let us say 5 states. So, imagine for a moment, imagine that you have a protein. Imagine that you have a protein which has 3 states. So, imagine that there is a protein which this can be one state, this is some other state, and let us say this is different states. So, the protein can have 3 states, let us say, and the energy in this state is E1, energy in this state is E2, and energy in this state is E3. Then the partition function Z is given by sum over I from 1 to 3, there are 3 states. So, 1 to 3 e power minus E I by kBt. This is the definition of partition function. This means that e power minus E1 by kBt plus e power minus E2 by kBt plus e power minus E3 by kBt. So, if you calculate this e power minus E1 by kBt plus e power minus E2 by kBt plus e power minus E3 by kBt, you will get a quantity, and that quantity is called partition function. And once you know the partition function, we can calculate many quantities. We will discuss that in detail, but this is the definition of partition function. E power minus energy in the state 1 by kBt plus e power minus energy in the state 2 by kBt plus e power minus energy in state 3 by kBt, and if there are more states, you sum like this for many times. So, what we have now is e power minus beta e by kBt by. So, let me write this once more. So, you have protein with 3 states, e power minus, let me write this as beta, where beta is 1 over kBt plus e power minus beta E2 plus e power minus beta E3. This is our partition function Z. Okay, now let us say we said there are 3 states for the protein. One is a state like this, one is a straight state, and one is a state like this. And let us say I am saying the energy of the state 1 is minus 2 kBt. kBt is a unit of energy. 1 kBt is about 10 power minus 21 joule. We can calculate this. kBt is a unit of energy. Let us say E2 is 0 kBt, does not cost anything to be like this, and let us say E3 is 5 kBt. So, these are values. Now, let us substitute this. So, if you substitute this E1 as 2 kBt, beta is basically 1 over kBt. So, the Z becomes Z is equal to e power minus beta times minus 2 kBt. So, e power minus minus will become 2 e power 2, and kBt and beta cancels because beta is nothing but 1 over kBt. So, e power 2 plus, if you substitute E2 here, this will become 0, e power 0 is 1. So, this is 1 plus e power 5, if I substitute, it will become minus 5. So, this is a number. So, partition function is essentially as a number. So, this is basically 1 plus e power 2 plus e power minus 5. So, you know e is a number, e power, you can take a calculator and calculate e power 2 and e power minus 5, you will get some numbers. E power 2 you will get something like very close to 9, something like 8 point something, you might get around 8. E power minus 5 you will get a very small number. So, this answer will be some number around 9 or 10, something like that number you will get. So, this is the rough answer you will get. So, Z is essentially a number. So, now what is the use of knowing Z? It turns out that the free energy is nothing but the log of partition function. So, it turns out that free energy F is kBt log Z. So, if you know the partition function Z, you can find the log of it and multiply with kBt and you will get free energy. So, Z is a number, log of Z will be some other number, and you multiply with kBt, you get unit of energy. So, if you know the partition function, it is easy to calculate free energy. So, if you know all the states here, you can take the log of this, and so in this case you have 1 plus e power 2 plus e power minus 5. So, if you the free energy of this system is kBt log of 1 plus e power 2 plus e power minus 5. So, this will be the free energy of that system of protein having 3 state like this. We said that this is E1 energy E1, this is energy E2, and this is energy E3, and sum over e power minus beta E1 plus e power minus beta E2 plus e power minus beta E3 gave us this, and then you multiply, take a log and multiply with this. So, you get this. Okay. So, once we understand the partition function, once we can calculate the partition function, calculating free energy is easy. We don't have to calculate entropy separately because we are summing over all possible states already here, sum over I. So, we are summing over all possible states, and multiplying with e power minus beta e. So now let's imagine that. So let's look at the definition once more. So we said that z is sum over I e power minus beta ei. If ei is 0 for all I, this will be sum over I. This will be just like z will be like total number of states. So z will be just total number of states, because I is equal to 1 to n e power 0. So this will be like e power 0 plus e power 0 plus e power 0 n times, where there are n states. So then a free energy will be kBt log z, which will be kBt log the number of states omega. Okay, so that tells us that there has to be a minus. So actually there is a minus sign, minus kBt log z. So this will become kBt minus log omega, and we know that kB log omega is nothing but entropy. So this part, this kB log omega is entropy. So this is basically T times entropy. So this will become minus Ts. So when energy is 0, the free energy has to be minus Ts, because we know that F is E minus Ts. We learned that F is E minus Ts. So if when E is 0, the free energy has to be minus Ts, and we got minus Ts. So just one thing is that we have to just say that free energy has a minus sign here. Okay. So with this, we understand how to calculate free energy, and we understand that this is nothing but the same as this. So we can calculate it both way. Either we can calculate this way or we can calculate this way, and you will get the same answer. So we know two ways to calculate free energy now. And now what is the use of? We will take some real example and calculate it also, and then we will also calculate what is the use of knowing all this. Now one more thing related to partition function we have to know. Now I said that when the system is in equilibrium, the free energy of the system will be its lowest, the minimum value. So then you can call it an equilibrium. That is a stable, when the system will be in a very stable equilibrium. Now let's think of, we will discuss some example, but before that, the modern view is that the system, for example a protein, in principle can go to all possible configurations. So you can find the protein in all possible configurations, but the probability of finding it in the equilibrium configuration will be much higher than other configurations. So the view in statistical thermodynamics is probabilistic. We don't say the system will be always in one place. We will say the probability of finding a protein in a given state is this much. So we can only talk in terms of probabilities, because the system in principle, if you wait infinitely long enough, if you put a protein and then wait millions and millions of years, or if you can wait infinitely long, the protein can take any conformation it wants. It can take all possible conformations. That is the view of statistical thermodynamics. So and that therefore, but the probability of taking certain conformations will be very, very, very small. It can be as small as like very close to 0. That means you will hardly see it. You may not even see it, or you might have to wait infinite time to see it. So now we have to ask the question, how do we know that what is the probability of finding a system in a particular state, let us say state 1 or state 2 or state 3. So we talked about certain proteins. So we said that, imagine that the protein has conformations like this, 3 conformations, conformation 1, conformation 2, conformation 3, and this is an energy E1, this is an energy E2, and this is an energy E3, and we said how to calculate z, which is e power minus beta E1 plus e power minus beta E2 plus e power minus beta E3. Now, you can ask the question, what is the probability that you will find the system in this state? And the answer is, the probability of finding a system in state I is e power minus beta, energy of that, divided by the partition function. So, if you know the partition function and if you know energy of a state, you can know what is the probability of finding the system in a given state I. So, we can ask the question, they have 3 states here. We can ask the question, what is the probability of finding the system in state 1, state 2 and state 3. So, probability of finding the system in state 1, let me call this P1, probability of finding the system in this particular state, which has an energy E1, is nothing but e power minus beta E1 divided by z. So, this is the probability of finding the system in this particular state. What is the probability of finding the system in this state which has an energy E2, and the probability that finding there is e power minus beta E2 by E2 divided by z, and this probability of finding here is e power minus beta E3 divided by z. So, now we have some values for z here. We said that the z can be calculated, we put some values, we said that the 3 states, the curved state, straight state and curly like this has energy, we said 2 kBt, 0 kBt and sorry, this is minus 2 kBt, 0 kBt and 5 kBt. These are the energies of this state, and we said that the partition function will turn out to be e power 2 plus 1 plus e power minus 5. Thus, e power minus 2 minus 2 will be 2 plus 1 minus 5. So, now probability of finding in this particular state, let us say probability of finding in this particular state, in the middle state P2 will be e power 0 divided by e power 2 plus 1 plus e power minus 5. That means, e power 0 is 1, so 1 by 1 plus e power 2 plus e power minus 5. This is P2. Similarly, you can calculate P1 and P3, and if you check, if you do this, so similarly you can calculate P1 and P3. Let us quickly calculate this. So, you can do this and you can see that, you will see that P1 is basically e power 2 divided by 1 plus e power 2 plus e power minus 5, and P3 will be e power minus 5 divided by 1 plus e power 2 plus e power minus 5, and we will see that P1 plus P2 plus P3, the total probability, this is the probability of finding in any of these 3 states, the total probability of finding is 1. So, we know this P1, P2 and you can see P3, P2 we wrote, which is e power 0, which is 1 by e power 2 plus e power minus 5 plus 1. So, the new denominator is same in all this, and new sum of numerator will become 1 plus e power minus 5 plus e power 2, and this will become 1. So, you can see that if you know the partition function, you can calculate the probability of finding the system in any state I, and from that you will get the total probability. So, now here you know this probability. So, you know how to calculate Pi, and from this once you know Pi, you also know, you might remember the formula of entropy, that which is Pi log Pi. So, the entropy of this system if you want to calculate. So, look at this here. So, you have this system, we know P1, we know P2 and we know P3, P1, P2, P3, and if you want to calculate entropy is easy. Entropy of the system is P1 log P1 plus P2 log P2 plus P3 log P3. So, we know P1, we know P2, we know P3. If you add this and multiply with minus Kb, you will get entropy. So, minus Kb log minus Kb P1 log P1 plus P2 log P2 plus P3 log P3, this will be the entropy. So, now we understand how to calculate various things. We know how to calculate partition function. From partition function, we know how to calculate free energy. We know how to calculate free energy if you know the entropy, and we know how to calculate entropy if you know if the system had different states, and if all the states had different energies. We just saw that in this particular way we could calculate entropy. Okay. So, now our aim is we yesterday calculated the entropy of a simple protein which had no particular energy. Now, we will think of one very famous model which can describe, for example, the conformations of DNA. So, this is an important question in biophysics in general. People have been wondering that if you have a piece of DNA in water, what will be the conformation of the DNA? What will be the most preferred conformation of the DNA? So, it turns out that it depends on the length of the DNA. If the DNA is very short or very large, it will have various conformations. But using the idea of statistical thermodynamics, we can compute, we can calculate what will be the most preferred conformation of a DNA of a given length L. Okay, now, this has a very popular simple model called worm-like chain model of a DNA, and we will briefly discuss that, and we will see how to calculate the partition function for this DNA, and we will see what we can learn from the partition function later. Okay, so, today right now we will discuss calculating partition function of a piece of DNA, and you know that once you know the partition function, we can also calculate what is the probability of the DNA shape being particular shape. And this has some importance, because like various contexts in biology, it turns out that for various gene for promotion, when various proteins repress or promote gene expression, the DNA typically forms a loop like this. So, this end of the DNA and this end of the two parts of the DNA has to come together for such that certain either gene expression or gene repression will take place depending on the context. So, you can ask the question, if you have a length DNA of length L, what is the probability that two parts of the DNA will come together? And the probability will be given by probability have to have this particular configuration C will be given by e power minus beta energy of that configuration divided by the partition function. So, this will be the probability to have this particular configuration. So, energy of that configuration divided by the partition function. So, if you know how to calculate partition function, you can calculate the probability that the DNA has a particular conformation. So, now we will discuss how to calculate partition function for the DNA in a given model. So, the simplest model for the DNA, you might have, some of you might have heard of this, called worm-like chain model. Worm-like chain model. So, this is a good model for double stranded conformations of double stranded DNA. So, the assumption here is that DNA can be thought of as a line for simplicity, which represents basically the center line across the double strand. We would not consider the complete double strand. It is to understand what conformation it will take, it is enough to think of DNA as a line. This is the assumption of this model, and if each point of this line you can have a, so if you have a coordinate, this is x and y, each point on this DNA can be represented by a vector, and this is 0 and this is the length of the DNA L, and you can think of one parameter called S, which is the arc length, the length along the contour of the DNA. So, if you this is S is a parameter, S something that varies from 0 to L. So, if it is here, the S is this much, S is the length from one end to that particular point along the contour. So, at every point, at any point S, you can draw a vector R from some coordinate system, and at any point you can also define a tangent vector. So, you can define a tangent vector here, which is del r by del s, the derivative of the r at any point we can define as tangent vector, and it turns out that this is a unit vector. Okay. So, the worm-like chain model assumes that the DNA is inextensible. If you apply some force and pull it, the DNA will not extend. This is an assumption of the model, and it turns out that for small forces, typical DNA of typical lengths, they do not show any stretching. So, based on this fact, it is assumed that DNA will not get stretched. So, worm-like chain model assume that DNA will not stretch. So, somehow, so this mod T is 1, this mod of this tangent vector. So, think of, so what are we saying now? DNA is a line, and you can define a vector at every point r, and the derivative of this vector is tangent vector. So, at every point you have a tangent vector. So, if you think of slightly more clearly, so you can think of DNA as a set of a line like this. At every point we can define a tangent vector. So, equivalently, this could be also thought of as a set of tangent vectors like this. So, this is the power of mathematics here, that we wanted to describe this idea through some equations. So, and we have a tangent vector. So, let me call this T1, T2, you can call it T3, up to there are n tangent vectors Tn. So, DNA could be thought of as n tangent vectors. So, each of the tangent vector could be one base pair long, for example, or you could take whatever length you one discretized unit as a tangent vector. So, typically you could think of it as each base pair as a tangent vector. So, and there are many base pairs organized like this. So, DNA could be thought of, or any protein in principle could be thought of as, any polymer could be thought of as combination of many subunits. So, in this particular way, DNA could also be thought of as a set of tangent vectors T1. Now, what is the energy of this system? So, it turns out that DNA does not like to bend. DNA like to be in a straight conformation. Beyond, if DNA is very short, it would like to be straight. If DNA is very long, it might be bending. So, to put in this fact that DNA does not like bend, if you want to bend DNA, you have to do some work. So, you have to put some energy to bend the DNA, and the energy depends on how much you bend these tangent vectors. So, it turns out that this can be, the energy can be written as E is equal to del T by del S whole square integral ds with some constant kappa. So, this is the bending energy of DNA. What is the logic behind writing down this equation? So, we want to write down bending energy, and the logic behind is that if the tangent vector changes, if there is no bending, all tangent vectors will be straight. Then the dt by the, and this is S is something varying from here to here. So, if as you go along the S, which is this distance. If the tangent vector does not change, then del t by del s will be 0. So, there the bending energy will be 0. On the other hand, if it is bent, the tangent vector would have changed. So, the del t, the tangent vector here is like this, here is like this. So, the tangent vector along the contour changes its direction. So, if the tangent vector changes its direction, then there is a bending, and therefore, the bending has to be proportional to del t by del s. Now, why is it square? Because del t by del s has different sign if it is like this or like this, but the energy to bend, if you take any filament, if you think of any filament, if you bend this way or this way, it's the same energy. If you assume everything is symmetric, if you bend this way or this way, it's the same energy. Therefore, the energy shouldn't depend on which way you bend it. So, therefore, del t by del s as a sign, we don't want that sign to come in the energy. So, we have the simplest way to put is square. So, del t by del s whole square, and the sum of this bending, this is a curvature basically. We discussed something about curvature earlier in calculus. So, this is curvature, and when we discussed, we said something about bending energy. So, this is a curvature energy, curvature and curvature, sum over curvature and multiply with a constant, and this kappa is called bending stiffness. Bending stiffness. If it is more, the bending stiffness is large for a, so this is applicable for many proteins also. So, depending on the system, if depending on the filament, if it is DNA, kappa has a particular value. If the filament here that you think of as a protein, kappa has a different value. So, kappa is a parameter that represent the property of the filament that we are discussing. So, for a DNA, kappa has a particular value. We will see what the value is. So, this is the bending energy, and we can convert. It turns out that this can also be written as E is equal to 1 minus T I dot T I plus 1 sum over I, and there is a kappa. There is a different kappa. So, let me call this kappa. So, let me call this E is basically some constant A times sum over I 1 minus T I dot T I plus 1. So, it can also be written like this. What does this mean? T I dot T I plus 1, if you have vectors, tangent vectors like this, T I dot T I plus 1 is the product between two tangents. If this is ith tangent vector and this is I plus 1 tangent vector, this T I dot T I plus 1 is the cos of the A dot B is A B cos theta. These are unit vectors. So, T I dot T I plus 1 is basically the cos theta, cos of angle between these two. So, it depends on the angle. If the angle is too much, cos of the angle is too much, more the bending energy. So, the bending energy can also be represented in this particular manner, or you can call this 1 minus cos theta I. So, you can write this also as A into sum over I 1 minus cos theta I. The cos of the angle, if everything is straight, cos theta will be 0, sorry, cos theta will be 0. So, cos theta will be 1 and 1 minus 1 will be 0. So, the bending energy will be 0. If the filament is straight, the bending energy will be 0. If the filament is bent with, there will be some angle, so there will have bending energy will have some particular value. So, this is the bending energy of a DNA in worm-like of the DNA in worm according to the worm-like chain model. Now, you know the energy. If you know now a particular configuration, we can calculate the energy. Let us think of some particular configuration of DNA. So, let us think of the DNA which is like this. So, let us think of first, let us think of DNA like this. So, this is T1, T2, T3, and here they are all straight. So, the angle is T1 dot T2 is 0. So, it turns out that the cos theta T1 dot T2 is cos of 0 is 1. So, the energy of this conformation is sum over I 1 minus T I dot T I plus 1, and the T I dot T I plus 1 will become just 1. So, this will become 0, the energy will become 0. If the conformation is, let us imagine some very funny conformations like this. So, the angle between this is 90 degrees. So, the energy of this, so there is 3 tangents and 2 angles. So, there is energy of this will be 1 minus cos of 90, and there is an A here, A into 1 minus cos 90 plus this also 90 degree, again 1 minus cos 90. So, cos 90 cos pi by 2 is basically, so cos 0 is 1, cos pi, so cos 90 is 0. So, this is 1 minus cos 0, cos 90 is 1. So, this 1 plus 1 is 2. So, let me write it a little more carefully this. So, what we want to calculate is basically energy of this. So, if DNA had this particular shape, the energy here is, the angle here is 90 degrees. So, energy is A into 1 minus cos, this angle is pi by 2. So, pi by 2 plus A into 1 minus cos pi by 2, and cos pi by 2 is 0. So, 1 minus cos pi by 2 is 1. So, okay, so there is also a minus sign here. So, the energy whatever we discussed, the discrete energy that we discussed has a minus sign. So, minus A into 1 minus T I dot T I plus 1. So, this answer will have a energy which is minus A into plus minus A, so minus 2 A. So, there is an overall minus sign for the discrete energy. It turns out that the bending energy we discussed, we discussed kappa times integral 0 to L ds del T by del S whole square. If we convert this to a discrete format, you will get E b as A times sum over I is equal to 1 to, okay, so there is no minus sign, this is correct what I wrote, 1 to n 1 minus T I dot T I plus 1. So, this is the correct answer. So, this you will get this answer, there is no minus sign here. So, this is plus the answer will be 2 A. So, there is no minus sign here, whatever we discussed is correct. So, A into 1 minus cos pi by 2 plus A into 1 minus cos pi by 2, the answer is 2 A. So, the energy of this system will be 2 A. So, these are the two energies in the discrete worm like chain model. Energy, bending energy is kappa into dt by ds whole square, and here it is in a discrete format, it will be 1 minus T I dot T I plus 1, where T I is unit vector. Okay, so, now if you know the energy, now we can think of calculating the partition function. So, the partition function is sum over all states e power minus beta e. So, we can write the partition function in two ways. Z is sum over I e power minus beta e I. We know E I for, or you could write it in a continuum fashion. Instead of sum, you can use an integral over all possible conformations. What is, so I'll explain to you what does this I mean. E power minus beta e. E will depend on the, so now what does this dt means? So, if you have a particular, this is one conformation, this is another conformation. So, one set of t, so this is T1, T2, T3, T4, this is one set of t. So, this is Ti, T1, T2, T3, one set of t will give you one conformation, another set of t's will give you another set of conformation. So, all possible, sum over all possible conformations. So, sum over all possible conformations is what it is. So, whenever I sum over I, this is sum over all possible conformations, and this is what this represents. You have to have a set of t's, and all possible set of t's will give you, and sum over this e power minus beta e, and e depends on this t's, the orientation of t's. That is why e wrote e bracket t, because e depends on t. You will get this. So, now how do we do this? So, now it turns out that if we can calculate this, we can calculate the partition function, and then we can calculate the probability of finding a DNA in a particular state. So, now let us quickly calculate this in the continuum format. It's easier to do it. So, let us understand what do we mean by all possible conformations. So, when we say all possible conformations, let us think of a simple example. Let us take this as your DNA. So, this is one conformation possible. This is like this. So, we have one base pair, another base pair. So, you have two base pair. This is one conformation. Now, if you have this base pair, if it changes a bit, this is a different conformation. This is a different conformation. This is a different conformation. Different conformation. So, this is, so I can go have a set of conformations here itself. So, by varying this angle, I can vary all possible conformations. Now, I can have slightly like this and have all possible conformations. So, I can have, when I say all, keeping this tangent constant, I can vary this tangent in all possible angles around all over this in 3D, and all of this is different conformation. This is a different conformation, this is a different conformation, this is a different conformation. So, when you think of a polymer with two monomers, by varying one of it, the monomer all over, you will get different. Then for each of this, you can vary this also. So, if you call this as tangent vector 1 and this is tangent vector 2, T1 and T2, integral of T1, the sum of T1 over all possible angles will give you all possible conformations. You integrate over, you sum over all possible angles, keeping the other one fixed. Then keeping this one fixed, you sum over all possible angles here, then that will give you another set of conformations, and for each of this you have all possible angles for this. So, the way to write it is, the first tangent vector dt1 can take any values, integral over all possible angles, and the second one also can take all possible conformations. The third tangent vector can also take all possible conformations, dot dot dot, and similarly there will be n tangent vectors. So, each of this tangent vector can take all possible conformations, and e power minus beta total energy, and total energy we know is A times 1 over T I dot T I plus 1 and sum over I. So, A into sum over I 1 minus T I dot T I plus 1 will be the energy, and this will give you this answer. So, now let us think about this dt1 a bit. So, I just said we just discussed that we can have all possible angles. So, now in 3D we can have, there are two angles phi and theta. So, we can sum over phi and theta. So, it turns out that the way of representing a 3D volume element, given that the length is a constant, is, so integral dt1 will be integral d phi 0 to 2 pi integral 0 to pi d cos theta. This will turn out to be the volume element, but we will discuss about that in detail in another lecture. But what I just want to say here is that we have to sum over all possible volume elements, and you sum over dt1, dt2 like this, you will get the conformation of all this. And if we know the conformation, then we can calculate the partition function for this particular DNA, and known the partition function, we can answer the question, what is the probability of having DNA in a particular conformations. So, if you want to have the closed conformation, we can ask the question, what is the probability of finding DNA in the closed conformation. Now, we know now how to calculate partition function, and we know how to calculate what in principle how to calculate the partition function of the DNA for a DNA under worm like chain model. We will do this explicitly in the coming lecture. We will explicitly do and calculate the partition function for DNA, and we will calculate some quantities that are of interest to us. But for the moment, we will stop with today's lecture here and then continue calculating in the next lecture. So, today's lecture, to summarize, we learned how to calculate partition function, we learned how to calculate free energy, and we also learned how to calculate the probability of finding the system in a given state I. So, with this I will stop today's lecture, we will continue tomorrow. Bye.